Okay, guys, I'm so glad at least it seems the video is recording and I checked the 2 minutes thing I recorded 5 minutes before and it is showing the PowerPoint. So I think I'm safe now. I'm starting and again, this video will be a little bit quicker because the first time I recorded it, I recorded very slow and I wrote down the proof, but it didn't show it since I already wrote down the proofs. So I will go through that with you and I'll make sure you understand them pretty well. Okay, let us share content, share an application window. Okay, now I'm assuming you all can see this. So you already watched the previous two videos at this time, and now I'll directly go into the definitions. So you know what is a multi-graph means? Now multi-digraph means you will just add a direction for each. So edge becomes an arc really. An Eulerian chain means, now when I use the word chain, please remember I'm talking about a graph. A path means a digraph. So, for example, take a graph. I give examples of just a graphs, but the same things are true for multi-graphs as well. And also the same things are true for digraphs also. But when you're doing diagrams, make sure you stick to the direction. You cannot go in any direction you want. You need to follow the directions of the arrow. So if the arrow is pointing in that direction, you're supposed to only travel in that way. An Eulerian chain in a particular graph is to be an Eulerian chain. That means first it has to be a chain, then it has to visit each and every edge across exactly once. You can visit the same vertex more than once, but you cannot travel on the same edge. So you need to visit all these, you need to travel through all these edges exactly once. So for example, I start at A, followed 1, 2, and then 3, and then this is 4, 5, 6. So now I visited. So it means I started at A. These are all vertices A, E, B, A, C, D, B. You see that I covered all the edges, but please remember I visited vertex A twice at the starting point and also 1, 2 at the end of third edge. That is okay. As long as I don't travel on the same edge, I can visit the same vertex over and over. That is absolutely fine. So this graph has an Eulerian chain. Now I'm going to talk about Eulerian closed chain or Eulerian circuit. A multigraph is said to be an Eulerian closed chain. That means you need to visit each and every edge across exactly once, but you will end up again at the starting point. Then you will say that graph has an Eulerian circuit or Eulerian closed chain, and in general you will call that graph as an Eulerian. So normally in textbooks they use the word this graph is Eulerian. What exactly they were saying is that graph has an Eulerian closed chain or Euler circuit, not path, not chain. It has to be a circuit or or a cycle, whatever you will call it, but you should start and end up at the same point. For example, let us look into this graph. This graph has an Eulerian circuit. You can see that in this case now I labeled the edges, not the vertices. Follow this edge A, B, C, and then D, E, F, G, H, I, then you'll follow J and K. So I traveled each and every edge across exactly once, and I started at this vertex and ended up at that vertex. So the first edge is A and the last edge is K. So this graph has an Eulerian circuit. So this graph is Eulerian. So what is we are trying to figure out is the necessary and sufficient conditions for the graph to be an Eulerian. Or if I give you a graph, can you figure out just by looking at the graph whether the graph has an Euler circuit or not? You might be thinking, okay, I'll try to figure out different ways of doing it. If I can do it, that is good. Otherwise, no, that means you're wasting your time. Without doing any work, just by looking at the graph, you should be can easily figure out whether the graph has an Eulerian circuit or not, whether the graph is Eulerian or not. If it is, I'm going to give you an algorithm which will help you to figure out. If it is not, you can just by look at it without even trying much, not wasting too much of your time, you can figure it out. The first thing is the graph has to be connected, because if there are some edges here and some edges far, you know that is not connected. So that graph cannot be Eulerian. So, but the graph is connected up to isolated vertices. That means there are some vertices which might be isolated with no edges can be there. Because in this case, we really don't care about vertices. We only care about the edges. So the edges all have to be together. They cannot be far apart. That means for some edges can be in this component and other component, it cannot happen. And also, whenever you enter a vertex, you have to leave. So whenever you touch a vertex, you are using two of the edges attached to it. So whenever you want to, starting and ending at the same point, the degree of each and every vertex has to be even, because whenever you enter, you better leave it. And also starting point and ending point are tied together. So these two are the necessary conditions. So if I give you a graph, you look at this, if one of them is not satisfied, then you will say that graph cannot be an Eulerian or doesn't have an Euler circuit. Not an Euler path. Euler path is a different ballgame. Euler circuit. I am starting and ending at the same spot. So that is what you need to do. Please remember. And for example, if I give you this graph, see the red graph, and I ask, does this graph is Eulerian? That means that is this graph an Euler circuit. You will see, okay, this graph is connected. All the edges are together. First condition is good. And but you see the degree of B. That means that means the number of edges associated to B, ooh, it looks funny, is now 3, 1, 2, and 3. I don't know suddenly why it became like this. Maybe it moved. Yes, this is good. So the degree of B is 3. So it is not an even number. So this graph cannot be Eulerian. So you can try it. You cannot start and end at the same spot by visiting each and every edge and every edge exactly once. Now the next theorem 11.2 in the textbook says these necessary conditions are sufficient as well. That means if the graph is connected and if the degree of each and every vertex is even, it has an Euler circuit. So this is both sides, it is true. Now I'm going to give you a very informal proof first, because your textbook doesn't give you formal proof, and then I'll give you the formal proof as well. Okay, now I'm going to give you an explanation for this. So the necessity I'm going to satisfy, assume that G is Eulerian. Now I want to prove that it's connected and the degree of each and every vertex is even. I think that is very straightforward. The graph is connected should be pretty clear to you, because if the vertex are someone one and someone other component, you cannot visit all of them and end up at the same spot. And whenever you enter edge, you need to leave as well. And also starting point and ending point are hooked up. The degree of each and every vertex is even. So the necessary, this side is quite straightforward, and the back side is where you have to do some work. For example, if I give you a graph and you know the graph is connected and you know the degree of each and every vertex is even, then now you need to prove that graph is Eulerian. That means you need to give me an Euler circuit of the graph. Okay, so this is sort of a constructive proof. I'm sorry, first time when I'm doing the recording, I wrote it and I'm writing and speaking at the same time. So that is a little bit slow. Now I already wrote it, so I'm going to use the same PowerPoint again. Okay, guys, this is a constructive proof. So now just remember the graph is connected and the degree of each and every vertex is even. Now I need to prove that the graph has an Euler circuit or the graph is Eulerian. Your textbook uses two algorithms 11.3 and 11.4 to prove it. So I'm going to explain both the algorithms to you with the help of an example, and then please read the algorithm. And this algorithm proves the sufficiency conditions as well. Then I'll give you much more formal proof, because your textbook doesn't give you any formal proof. Okay, the algorithm 11.3, this name is closed chain x comma x. That means you will have a multigraph, and if you follow this algorithm, you take any vertex in the graph, say x. If you mimic this algorithm, you will get a closed chain from x to x. It might not cover all the edges, but you start at x and you visit each and every edge, not each and every edge. You visit couple of edges and you'll come back at x. When you use the word chain, means that itself will tell you by definition you cannot travel on the same edge twice. Okay, this is closed chain x comma x, and this is on page 618. Okay, this is algorithm 11.3. Please remember the graph is connected. Degree of each and every vertex is even. Let us take this graph. This graph is on page 633 and figure 11.20. Okay, guys. So now this algorithm says is close your eyes and pick any vertex from the graph. That is your x. So in this same, I closed my eyes and pick C. Now I'm going to give you a closed chain which starts at C and ends up at C. So what this algorithm simply says is this. You start at C and pick any. That is what this algorithm says. So pick any now. Choose any neighbor of C and look, pick up the edge connecting to C and that neighbor. So C has two neighbors, B and D. Pick anything. It doesn't matter which one you pick. Maybe I'll pick B. So now take this edge C comma B. Now look into the neighbors of B and connect and pick an unused edge. B has neighbors C, D, and A. Among this edge is already used. So now pick either this or this. One of those edges. I'll pick BA. Try to color with black. Hopefully you can see that. Now look into all the neighbors of A. So that is B, G, and F. And AB is already used. So pick other two edges. So I picked AG. Now look into the neighbors of G and pick an unused edge from G. And you keep doing this until you hit C. Once you hit C, then you stop at that point. So after G, I travel to E. After E, I travel to D. After D, I travel to C. So this algorithm will give me this output C, B, A, G, E, D, C. But still, this is not an Euler circuit because you haven't used all the edges. You used only the edges which are colored in black. Now algorithm 11.4 simply says do this procedure couple of times. Once you form one circuit, one chain or whatever you call it, a circuit, closed chain means a circuit, and see whether all edges are covered. If all edges are not covered, then just remove these edges from the graph. That means mentally delete these edges from the graph. So then you will get the graph without these edges. You will not have these black edges in the graph. Just mentally you try to draw on a scrap paper, you can see that. I think the graph is going to look like this. B will be there for sure, and B to A will be there like this. So again, the graph might not be connected at this point. Graph might not be connected, but that's okay. But of course, this graph is going to be connected even if you remove it. But the graph need not be connected. So try to sketch the graph. Just remove these black edges and try to sketch the same graph. Just remove these edges. Remove edges C, B, B, A, G, and I'll draw the graph. And if you observe in that graph also has an even graph. That means the degree of that graph is degree of each and every vertex in the graph is also even. The reason being in the original graph, the degree of each and every vertex is even. Now I removed a cycle. That means each degree is either goes down by 0, that means the vertex is not there, or the degree of that vertex is goes down by 2. For example, the degree of B is goes down by 2. Originally the degree is 4, now in that the resultant graph the degree is 2. So still the graph is an even graph, and at least there is one vertex in this cycle which is in that graph whose neighbors are all not covered, whose edges which are incident with that are not covered. For example, if you take A, in AB is already there, AG is already there, but AF is not there. So take any vertex. You can take either C, B, A, it doesn't matter. I picked A. Starting at A, apply this algorithm again on the other resultant graph. That means in this particular graph, start at A and cover all the, follow this algorithm, and it gives you a closed chain starting at A and ending at A. So I start at A. Now the resultant graph will not have these black edges. So I picked AF and then F has two neighbors. F has this one, or this one. I can pick any of those wedges. I picked this FE, and then E has neighbors in this graph. In this case, only choice is D. Now, again, please observe, in the previous also I do ED, but now I'm using a different graph, ED, different edge. And D has a neighbor. Now it has only one choice because the black edges were all not already covered. EB, and then B to A. Now I got this blue cycle. Now I observe, is all the edges are covered? The answer is no, because some edges are not covered, the green ones. Now I removed these black and blue edges from the graph. Now there is at least one vertex in the graph whose neighbors are not covered. Otherwise, the edges, the graph might be already an Eulerian circuit. Since I didn't get an Euler circuit, that means there is at least one vertex in the graph, and all the edges adjacent to it are not covered. For example, in this case, F, these neighbors are not covered. So I start at F, and I want to apply algorithm 11.2 again. It gives me a closed chain from F to F, the green one. Now all the edges are covered, so I am good. Now you can form your Euler circuit on the original graph like this. Starting, you take the black circuit. This is the one. C, B, and the first time you hit A, now start the blue path, A, F, and the first time you hit F, and then follow the green path, F, H, F, and then E, D, B, A. Once I'm done with this, and follow this direction. So I follow the C, B, A. Once I hit A, I need to follow the blue one, A, F. But once I hit F, the first time I hit F, I follow the green one, A, F, F. Since I finished with the green one, I'll come back to the blue one, F, E, D, B, A. That means now I finished the blue one, then I followed the black one, A, G, etc. So now the Euler circuit for the original one, C prime, is given by C, B, A, F, F, H, F, E, D, B, A. Now I'm starting here, then G, E, D, C. So whenever I hit the first time, when I hit the blue vertex, follow that one, and first time I hit the green vertex, follow that one. This is what algorithm 11.4 will tell you. So you get the Euler circuit for the entire graph. Hope I made some sense to you. So I'll give an example and it gives you much more sense in the assignment. Now I'm going to give you more formal proof for that. In the textbook that doesn't talk about, because this is actually a great proof. Now I'm going to give you much more formal proof explaining the same thing. Now to do a formal proof, I want to give you a small lemma. This lemma simply says, take any graph, it need not be an even graph. If you know the degree of each and every vertex is at least 2. This has nothing to do with the previous result at. It is not an even number, I'm saying. The degree can be 2, 3, 4, 5, it can be odd numbers, but the degree of each and everything is at least 2, then G should have a circuit. Now I'm saying, take the maximal chain in G. That means take a chain in G which cannot be extended further. I'm not saying this is the biggest possible chain. I am simply saying this is the maximal chain. For example, your graph might look like this. This is your graph. This one, A, B, C, is a maximal chain because I cannot extend it. But this is not the longest possible thing. I have A, B, C, and then say D and E. There is another bigger path than that, but A, B, C is a maximal path because I cannot extend that further. And take an endpoint of the maximal path. I'll call that as U. Since this cannot be extended further and the degree of each and every vertex is at least 2, so G should have at least one more neighbor V which is in the path, because this cannot be extended. So all the neighbors are within the path again. This is my path P. So I should have a neighbor V in P, when a vertex of P, via an edge not in the P. It should have an edge via not in P. Now take this edge UV and take the portion in the path which will give you a cycle or a circuit. So this is the lemma. So I will use this lemma and proving my result. Now I'm going to give you the formal proof. of 11.2. Again, don't worry to memorize the proof, try to understand. Now the algorithm 11.3 and 11.4, I'm going to formalize it and give you a proof. Again, I'm not going to ask you to write like these things in the exam, so don't worry about the exam purpose. Try to enjoy the proof if you can. This 11.2 says a multigraph has an Eulerian closed chain if and only if G is connected up to isolated vertices and degree of each and every vertex is even. Now the necessity condition, that means now you're assuming your G is Eulerian. That means now I'm saying every time you go through a vertex in C, you need to get in and get out. So you're using two of the edges which are incident to that. And also first edge is paired with the last at the first vertex. So every vertex has an even degree. And if you want to use all the edges, because in the Euler circuit you use all of them, better they all in the same component. So there must be only one non-trivial component. So necessity is comparatively very straightforward. The backward direction is where normally you do some work. Now you assume at this point the graph is connected and the degree of each and every vertex is an even number. Now you want to prove there is an Euler circuit in this graph. This graph is Eulerian. Now I am doing this by using mathematical induction. I'm hoping you have seen math induction before. You will prove the result for the base case, and now you assume the result is true for some m, and then you will prove the result for m plus 1. That is the concept of mathematical induction. I'm assuming you have seen that before. In this case, most of the base cases people take as m as 1, but I'll take m as 0. Here I'm doing induction of the number of edges. When m is 0, that means there are no edges. That means there is only one vertex. So of course, by default, that is Eulerian because that is called vacuously true, because there is nothing to prove, so it is true, kind of a thing. Assume the result is true for some m. We need to prove the result when the graph has more than m edges. So take a graph with more than m edges, and you know the graph is true, the result is true if the graph has m edges or less. Now, since the degree of each and every vertex is even, so you know the degree of each and every vertex is at least 2. So by the previous lemma, that graph should have a cycle. I'll call that cycle as C. This is 11.2, the closed chain from X to X. That is what lemma is saying. Lemma is precisely the formal proof for 11.2 algorithm. The 11.2 algorithm is on page 634. Sorry, algorithm 11.3. I will write it down here. This is a proof of algorithm 11.3. Really, that's what this proof is. Now I'll come back here. So that's what I'm using 11.2 to get this cycle. That's what I'm doing. Now I'll remove the cycle. Now the resultant graph is called G prime. G prime is the graph obtained from G by deleting all the edges. Now the graph might completely get disconnected. That's okay. That means the graph can get one piece like this, one piece, one piece, one piece like that. That is absolutely fine. But since you removed a cycle and the degree of each and every vertex was even before, and the edges you removed is cycle, so the degree of each and every vertex is go down by 0 if that vertex is not part of the cycle, or goes down by 2 if the vertex is part of the cycle. So the graph G prime, which you got by deleting all the edges, is also an even graph. Suppose the graph looks like this. This is one piece, this is one piece, this is one piece, and this is dotted black thing is the circuit C you removed. Now our result says, now if you take each and every piece, either this piece and this piece and this piece, the middle one, these are all graphs by themselves, and each and everything has total number of edges less than or equal to m. So my induction hypothesis, I can find an Euler circuit in each piece. That means I had an Euler circuit here, all the edges are covered here, Euler circuit here, and an Euler circuit here. Again, I'm just giving you a very rough graph here. This is no means a graph. I don't know how the graph looks like. Now I am saying take these Euler circuits, the red ones, and I'm attaching to this dotted black one, C1. That's what I'm doing. We traverse the C, but when a component of G prime is entered for the first time, we detour along the Euler circuit of that component. All it is saying is this: I start at this point, I keep on traveling. Once I hit this spot, I travel this, I take a detour here, and I visited all the edges by following the Euler route and come back at the same spot. And then I keep on traveling. And the first time I hit this, I take a detour and visited all these edges and comes back. And then I'll keep going. Once I hit this spot, I visited all these edges by following this Euler circuit and then come back and come like this. This kind of adding things is going to give you an Euler circuit of the entire graph. That is what this says. This is the formal proof. This is only for the Eulerian closed chain. If you want the result for an Euler path, then that result is theorem 11.3. That is theorem 11.3. Again, they haven't given the proof and I'm not giving the proof. Please read the statement. All this says is a multigraph has an Eulerian path or an Eulerian chain. It's not closed anymore. That means now you have to visit all the edges, but you don't need to end up at the same spot. Now you have a little bit of the freedom. The graph should still be connected, but the degree of each and every vertex need not be even, because the starting point and ending point might have an odd number, odd degree. That means the graph might look like this. See, the degree of A is 3, the degree of D is 3, and the rest of the vertices have an even degree. Still, this graph doesn't have an Euler circuit, but this graph have an Euler chain. Since the degree of this A is odd and D is odd, so I need to start either at A or at D and end at the other way. So I can take this A, this is the first edge, second edge, third edge, fourth is this, fifth, sixth, and this is seventh. So I started at A and I followed like this and ended up here. So the degree of vertices of odd degree should be starting and ending points. That is what theorem 11.3 says. They haven't done the proof, so I just want you to read the statement. And the similar results are true for the digraphs as well. But when it comes to the digraphs, the theorem statements are in 11.4 and 11.5. Oh, battery is running close then. It is simply saying the graph has still to be connected, but the in degree is same as out degree. That means if you take this graph, the in degree is 2, 2 edges are coming, 2 arcs are coming in. Sorry, in degree is 3, 3 arcs are coming in, and 2 arcs are going out. Out degree is 2. So if you want your graph to be Eulerian, whenever you want to get in, you need to get out. So the in degree should be equal to the out degree. So please read theorem statements 11.4 and 11.5. And I'm going to post 1 or 2 more videos in few minutes on section 11.6. And section 11.4 is just an example. I'm going to post an assignment on these things. Read section 11.4 by yourself, but don't read all the applications. Read the questions I'm asking and only read the applications which will help you to solve that particular problem. So if you have any questions, I'm more than happy to help you out. Please email me. So I'm going to stop sharing before my battery is dead. And I'll come back to this.